In this example, we've got a thin homogeneous bar, mass M, length L, and we've drilled a hole in the bar there at point O. We put a pin joint there, and we're going to release this bar from rest when it's in a horizontal state. And what we want to find out is once we let it go, what's the angular acceleration of the bar, and what is the reaction force there at O, at the pin. So let's look at our FBD. Forces we have some reaction forces here at the pin joint, OX and OY. At the midpoint of the bar, it's a homogeneous bar, we have mg, and I'm going to use x to the right and y positively up. Newton. Well, we know that we have three equations which are going to come from our Newton-Euler equations. If I sum the forces in x first, I see that the only force acting in x is OX, so that is equal to mAgx. Some forces in y have the reaction component there of OY minus mg, and that's equal to mAgy. And lastly, we have a moment equation. Here's a problem where we actually have a choice. If we want to set moments equal to I alpha, we could use either the center of mass as we've done before, or we can use a fixed point. Use the fixed point whenever you can. It's usually the easiest way. So since O is a fixed point, I'm going to do that. I see that the only force causing a moment about O is the weight mg. It has a moment arm of 0.2 L, and it's in the positive K. That's equal to, and be careful, that's equal to mass moment inertia about O times alpha. So those are the three equations that come from our 1FBD kinematics. Okay, so what we want to do actually is relate the acceleration components AGX and AGY back to alpha of the bar. So my suggestion is to say AG is equal to AO plus alpha cross R minus omega squared RG with respect to L. The reason for picking O is that it's a pin, so we know its acceleration is a 0. Alpha, that's an unknown. I'll just leave that as alpha k. And the vector which goes from O to G is going to be minus 0.2 L in the eye. Omega, it says it's released from rest. So what we have here is a minus 0.2 L alpha in the J. What's the point? Well, the point here is that there's no x component of acceleration of G. The y component, which we need, is equal to minus 0.2 L alpha. So that's going to be our fourth equation. Probably now is a good time to do the mass moment of inertia about O. So we'll also say that by using the parallel axis theorem, P.A.8, we see that I.O. is equal to I.G. plus md squared. D is the distance between O and G. Okay? So Ig we know is 1/12 ml squared. The distance d, that's 0.2 L, so that gets squared. So it's going to be 1/12 plus 0.2 squared times ml squared. So don't forget that. took the good route, I think, by doing a moment about O, but we pay the price here and having to find the mass moment of inertia about O. Okay, so we're in good shape. We can now solve. Equation 3 says that alpha is equal to 0.2 mgl divided by IO. We have that. So whatever number that ends up being, we know it's a plus, and that's good. The plus sign means it's counterclockwise. We made that guess, and the guess was right. In order to find OY, so equation 2 then, the reaction force at O is going to be mg plus AGY. AGY we saw was equal to a minus 0.2 times L, and alpha, that's 0.2 mgl divided by IO. And that all gets multiplied by m, so let me make that a square bracket like that. So that tells us what OY is. Equation 1, OX we said was equal to mAGX, and that was a 0. Okay, so those three numbers came straight from our Newton-Euler equations. I had to do the FBD first, not too bad. Just the reaction forces there at O and the weight. Some forces in X and Y, did a moment equation. I chose to do it about O, a little bit simpler than doing it about G, because we were able to get alpha in the end with one equation. The kinematics, we went from O, the fixed point, over to G, and found out that the y component of AGY was minus 0.2 L alpha, and AGX is a 0. And don't forget the parallel axis theorem. The price we pay again for doing a moment about O is we need IO, not IG. And basically solving those three equations for alpha, OY, and we find that OX is a 0.